Okay, 1.4 day 1, we're going to review linear systems. Later in this section, we will add 3 equations instead of 2 equations, which will be a new thing from Algebra 1. Okay, let's look at linear systems. For a linear system, you can have one solution, you can have no solution, or you can have infinite solutions. Most of the time when we ask you to solve it, there's one solution. Normally, if you were graphing a system, you would have a line and then another random line. I'm putting it randomly. The solution to this system is the point where they intersect, which would be right here, and then I would write my answer as x comma y. Okay, when you solve this algebraically, you get x equals this, y equals this, and then you write your solution x comma y. Okay, and most of the time when we ask you to solve, that's your answer. Now, occasionally there is no solution. So on a graph, I'm thinking there has to be 2 lines, and there has to be no point in common. Okay, so let's draw this line. Okay, my second line needs to be drawn such that there is no point in common. So I'm going to make it exactly parallel. So if the lines are parallel, they have no points in common, therefore there is no solution. Okay, algebraically, if I was solving something and the answer was no solution, the variables would eventually cancel out and I would end up with something like, let's say, 5 equals 3. Which is not true and doesn't make sense. So the fact is that 5 does not equal 3. So since it's a not true conclusion, the entire system is false and there's no solution. Now, how do you get infinite solutions? Okay, let me start out with my first line, which is randomly drawn. Okay, for it to be infinite solution, there need to be billions and billions of points in common. Infinite. So there need to be like this point, this point, this point, this point, this point, all these points in common, which means the second line needs to be exactly on top of the first line. That way the points in common are every single point on the line. So there's infinite solutions that happens to be all the points on the line. Algebraically, if you're solving an equation that has infinite solutions, you end up with some kind of true statement that means every point on the line makes the system true. So instead of 5 doesn't equal to 3, we might get like 5 equals 5, which is always true, which means there's actually infinite solutions, and this system is always true for every point on the line. Okay, so for the first ones, I'm going to solve them by graphing. I'm going to show it now. Go ahead and pause the video and graph them yourself and see what your solutions are, and then unpause to check your answers. Okay, ready to check your answers? Okay, for number 1, I drew my 2 lines. They intersected at 4, 2. For number 2, I graphed y equals 2x minus 3, y equals 2x plus 1. They do not intersect. They're perfectly parallel, and I could tell because the slopes are both 2. So there's no solution. There is an abbreviation for no solution, so I wrote no solution. But the abbreviation for no solution is a 0 with a slash, and it means that the solution set is empty. Okay, and then for the last graph, I graphed the first one and I graphed the second one, and they're exactly on top of each other. So every point along this line is a solution. So there are infinite solutions. There is not an abbreviation for writing infinite solutions. I know there is a symbol for infinity, but when you write infinity, you're saying infinity is the solution, which it's not. So we're going to write infinite solutions. Okay, now go ahead and start solving these systems algebraically. You could use elimination or substitution. Not the catch, but the fun part is that some of these will have no solution and some will have infinite solutions and some will just have an ordered pair. Okay, go ahead, pause the video, try to solve it. When you get stuck, unpause. I'm going to do 4 and 5. Okay, for number 4, I used elimination. I got 2, 1 as my answer. For number 5, I didn't quite solve it, but I'm about to. I'm going to use elimination. I multiplied the first one by -3. Okay, I'm now going to bring this down. This is going to cancel, and this is going to cancel. So what's left over there is nothing, which is 0. Okay, I'm going to add up the right side. -12 plus 8 is -4. So 0 equals -4 is my final statement. Is this true or false? It's false. So what does that mean? It means the entire system was false. So this is no solution. Or you can do the 0 with the slash. Okay, but you do need to show the work all the way till you get to the false statement, because that's how you make the conclusion that there is no solution. Okay, go ahead, flip it over and try the back. Okay, for number 6, 0 equaled 25 is not true, so it's no solutions. For number 7, I'm about to finish it. I did elimination. I multiplied by -2. Okay, when I do that, this cancels, so I'm left with 0. Equals, if I do -18 plus 18, I also get 0. Is 0 equals 0 true or not true? It's true. It's always true. So this is infinite solutions because it means every single point on that line or either of those lines will make this true. So this is what it would look like when I get infinite solutions. Okay, go ahead, keep going. Unpause when you're stuck. Okay, for 8, I got 0 equals 0, which meant infinite solutions. Make sure you show that this step to show that you've gotten to a true statement. For 9, -6 comma 1. Okay, for 10 and 11, I use the substitution method. For 10, I plugged it in. I have 5x minus 5x, which cancel. So I get 2 equals 4, which is not true, so this is no solution. For 11, I also did substitution, and I got 4, -3. Okay, and then for 12, substitution again. Again, the -6y, +6y canceled, so I got 10 equals 10, which is always true, so infinite solutions. And then for 13, I did elimination, and I got 3, comma 1.